So this presentation, this talk is about software development in 100 years' time, and you're probably correct in saying that's a little bit hubristic. But this is, I'm not going to be talking about the amazing things that will be different in 100 years' time, as much as what are the ideas that are durable, what are the kinds of ideas that are still going to be true in 100 years' time. And in part, this was inspired by a conversation that I had. I've been talking about software development for a little while now in various contexts, and I was engaged in a conversation on Twitter a couple of years ago, and somebody said, and we were talking about software engineering and what engineering really means for our discipline, and this person said that if we were able to come up with genuine engineering disciplines, they would be as true in 100 years' time as they are today. And that kind of resonated with me. That kind of had an impact with me. The other angle to this is I'm assuming that we'll be better at it in 100 years' time. So what are the things that are going to allow us to create bigger, more complicated, more advanced systems than we do today, that we could perhaps predict? And really that's the theme of my talk this morning. I think the good starting place, if we're looking to extrapolate forwards and think about what software development will be like in 100 years' time, is to think back to what software development was like 100 years ago. And if you're anything like me, you're probably thinking something like this, is that there was no software development 100 years ago. And sure, there were no electronic computers, but there was something that was close. There were several things that were close. One of those is represented in this picture. This is a Hollerith machine. This is the machine that was used to help tabulate the data from the US Census at the start of the 20th century. And this is a computer. This person had the job of being a computer. That's what her job was called. And she's doing programming, and she's doing programming for the Hollerith machine. You can see the same device on her table as on the table of the Hollerith machine over there. What she's doing is she's programming by punching holes in a piece of card. The piece of card in the picture here is a more modern version of a punched card, because I couldn't find a picture of the punched cards from the Hollerith machine, but the principles are the same. What's kind of interesting is that you can write down the algorithm for the Hollerith machine in SQL, and pretty much this is it. This is what's going on here, and I think that this is one of the first kind of insights. Is that this is the kind of thing, the kind of idea that we would capture in code today. There's nothing really changed in terms of the level of abstraction of the idea that we need to encode in some way. They're not different, the ideas, in essence. We would be composing more complex systems over little pieces that look like this today, rather than just one piece. But nevertheless, there's something about the level of detail that we need to express in order to capture something computable. And sure, writing it in SQL is more efficient than holes in a piece of paper, but I'm going to come back to that idea of kind of trying to capture that level of abstraction, because I think there's something there. At the heart of my presentation, there's kind of one big assumption. And the big assumption is that it's us that's doing the programming and not them. Because I think in 100 years' time, it's very likely that they'll be doing at least some, if not most, of the programming by then. But I'm assuming for now that it's still us, and we've still got to cope with the problems. So the assumption that I'm working on is really this, that software still needs to fit inside a human head. We still need the capacity to understand the systems that we're going to create. And that's what I'm going to talk about a little bit. So let's start thinking about some of those ideas, some of the ideas that both might help us to cope with more complexity and bigger more sophisticated systems, as well as being durable, as well as maybe last. And the first candidate for that is programming language. And I don't think so. I don't think that programming language is going to be the thing. I think it's probably not going to be durable. There probably will still be some Java around in the corners, maybe in 100 years' time, and some JavaScript maybe, and probably still some COBOL, I don't know. But I don't think that most programming will be done in modern languages. But I also don't think that the change is going to make a significant difference to our productivity or the level of sophistication of the systems that we can build. And that's in part because I don't think we've made as big a jumps as perhaps we sometimes think about in terms of language. So first, why do I expect that there will be new languages? Well, people really like writing new languages. There are lots of them, and there are lots of them all of the time. And if I'm absolutely honest, I think there are only a few that have made a significant difference in productivity. The last significant change in productivity that I can think of, a big jump, was probably managed environments and popular garbage collection. That's an idea that goes back to the late 50s or early 60s, around that kind of time, garbage collection, but it became mainstream, probably late 90s. The step from kind of machine languages to higher level languages was a significant step. Structured programming made a difference. Object orientation made a difference. Functional programming made a difference. All of those ideas are 1950s ideas. So I'm not sure that we're making the kind of advance that we think we are in terms of languages. We play with the syntax, and sure, some of the syntactic changes are a little helpful, but I don't think they're the kind of thing that gives us orders of magnitude improvements in the capacity of the systems that we can cope with. I think those are other kinds of problems. So I don't think that language is likely to be the thing. If I'm honest, I saw a presentation by Bob Martin recently who said that he thought that all of the language paradigms had probably already been invented, and he made a reasonable argument that might be the case. And so I don't think we're seeing big jumps these days, and haven't done for a significant amount of time, in terms of the effectiveness of the languages that we create. So I think that mostly language design is about fashion. It's about preferring, some particular features in a language, but I don't think we're getting big jumps in effectiveness from those. So my prediction is that there are going to be no great leaps in productivity because of programming language. I don't think that elusive striving for a different level of abstraction is there to be had at this kind of level. I've just said that. I don't think there's going to be this huge level of abstraction. And the Hollerith machine is an example. We still need to capture ideas at roughly the same level of granularity to encode them in a programming language. And which programming language you choose to that might make a small difference in the number of characters you type, but I would argue it doesn't really make much difference in the level of thinking that you need to apply. The next on my list of candidates is frameworks. And again, I don't think so, but perhaps with some caveats for both language and frameworks, which we'll get to. But I think that frameworks too are not the panacea that we often think that they are. I am in the midst of writing a book at the moment about some of the ideas that I'm talking about in this presentation, but in the context of software engineering. What is modern software engineering? Is the theme. And one of the exercises that I thought would be interesting to undertake, which I haven't completed yet, but I'm part way through, is to write a simple CRUD web application using modern technology. So I picked Angular. So I'm writing a modern web application using Angular and I'm writing the same application in technologies that were available to me around about the mid-90s. So JavaScript, Java, HTML, CSS, those sorts of technologies. And so far, my CRUD application is about a quarter of the code in old-fashioned technologies than it is in Angular. I think that's probably not what most of us would expect, but I think that's fairly common, that the frameworks often don't deliver the kinds of savings that we expect. I remember seeing a fantastic presentation from a few years ago from a GOTO conference, which was comparing software development with making cakes, and it was saying professional chefs don't use cake mix was the name of the presentation, and it compared using Hibernate, the Java ORM library, with writing SQL, and demonstrated that the SQL was shorter, simpler code than using the ORM to do anything of any complexity. So I think that people like writing frameworks too, so there will continue to be lots of them, but I think that they often don't give us the savings that we are probably anticipating or expecting. So why not? Most frameworks, I think, focus on the wrong things. I think that this is also true of languages a little bit, is that they're mostly focused on trying to optimize for less typing. And I don't think that's the problem. I think if my typing is bad enough to be the constraint on my programming, I'm doing it wrong. I should learn to type. I think that what's more important is trying to optimize for better thinking. And I think that's a more successful strategy. So my prediction, my caveat, I think that there may be some big steps facilitated by frameworks, but only in combination with a bigger rethink on design, architecture, and programming model. So what do I mean by that? Part of that I think that we can see in the advance of cloud computing and the change in abstraction of things like operation. That is one take on that move, is it's a move towards greater separation of the accidental complexity from the essential complexity of a problem. And that's a good thing if we can do that, if we can kind of move the accidental complexity of executing these things on a computer to the edges of the system, and are more able to focus on the essential complexity of the problem that we're solving. That's going to be easier to create those kinds of systems. So I think there's stuff that we can certainly do, but I think that frameworks alone are not enough. We need a deeper think about the way in which we organize the ideas that we are trying to capture that represent the software systems that we're building. The next in my list of, I suppose, straw men is programming paradigm. And again, I don't think that programming paradigm is going to cut it. And I've already said part of the reason for this is that it's not obvious to me where the next programming paradigm is going to come from, and the ones that we have been around for a very long time. We haven't had a new programming paradigm introduced for a very long time. So we think of functional programming as the newest programming paradigm, and it's not. Functional programming was described pretty accurately in 1957 with the invention of Lisp. It's taken a long time for it to become more widespread and more popular, but that's a different problem. That's not about the paradigm itself. So I'm not convinced that programming paradigm is going to fix it. Again, this goes back to this idea of there seems to be something fairly durable about the level of detail that we need to specify in order to express ideas in code. I've been working in software development as a professional for something around 40 years. And during that time, I've seen a number of different attempts to try and raise the level of abstraction. The commonest approach to that kind of problem that I've seen several, but the commonest approach that I have seen has been to try things like visual programming, trying to somehow interpret diagrams and make diagrams executable or pictures executable in some way. And those things usually demo really well, but as soon as you start getting anything to any kind of complexity in the problem that you're trying to capture, code is more efficient. So you can kind of see this in the how hard it is to capture something as simple as a for loop in UML. You know, it's not an idea that maps nicely. UML can be a useful tool. I'm not knocking UML, but it's not as good in terms of expressing executable intent as code. And so I think trying to identify something in that level of abstraction that's going to give us the ability to create significantly more complicated systems, which I'm assuming that we will be doing in 100 years' time, is going to come from programming paradigms. So my thinking is that in 100 years' time, programming will still be procedural, object-oriented, and functional in parts, because each of those paradigms brings something to the party and contributes something, supplementing the others. As an aside, I saw an example recently of a popular kind of theme, which is functional programmers pointing out that OO is flawed and defunct. And I'm an old school OO programmer. And so I watched those with some amusement. And in this example, the person was saying, look, I can do all of this algorithm with a simple map and a fold over the map. And going through my head was, where do you think the idea of capturing a map so it looked like that came from? Because that's OO thinking. So I think that that these ideas supplement one another and complement one another. So a controversial opinion, as I said, I'm an old school OO programmer, is that the current fashion to downplay the value and impact of OO is primarily a religious war. I think that I've heard people say that OO failed, and I think that's just nonsense, because OO allowed us to build different, more complex kinds of systems. And if you look at any modern operating system, and most modern systems, at some level, there are ideas that were taken from OO thinking at their heart. OO was an enabling step. And I think it also, from a personal point of view, I think one of the values that it brings that I don't see as much in functional programming, and this might be my bias, but I think that OO provides a mechanism for giving you a navigational space in your problems that is hard to find in the other paradigms. So my controversial opinion is that OO is still going to be around, perhaps. One area where I think that there might be a gap, and there is room for capturing something, is the idea of services. And I think that services and service-oriented architecture is an important idea that isn't really surfaced to a large extent in the languages that we use, and even to some extent in the frameworks that we use very often. If you think about encoding a service of some kind, whatever that means to you, you don't have language support for that very often. There's nothing that clearly delineates the boundary of a service in your programming language or in your code and the inside of the service, or the inside of another service. We do that by convention rather than by language or explicit framework support. I think that is likely to change, and I think that moves like serverless, perhaps, and one of the areas that interests me, which is stateful serverless, might change that. I think stateful serverless gives us an opportunity of building things that I would call reactive systems. And if you're interested in what I mean by that, there's a thing called the Reactive Manifesto that describes some of the properties of those sorts of systems. So I think that we're missing that important level of abstraction. Service orientation's a valuable idea, and certainly an idea that's impacted on my career for a significant proportion of it. The next in my list of candidates is test-driven development, and you might, depending on your background and your approach to software development, you might question me putting this in the same kind of category. But I think that test-driven development is one of the more important engineering disciplines that has been invented during my time. Nevertheless, I'm kind of encoding this amber rather than red. I think it hasn't taken off in the way that I probably expected that it would when I first got exposed to it. And there's a good reason for that, and it's primarily because we got the words wrong. Nearly everybody, when you talk about test-driven development, focuses on the word test. And a better focus is on the word driven. Test-driven development isn't really about testing. It's about driving design through tests and taking an approach. It gives an independent path evaluation of our changes. Nevertheless, it's not become ubiquitous in the way that I think that it should do. I think though, in 100 years' time, something like it will be a cornerstone of software engineering, but it probably won't be called test-driven development. And the reason that I think that that is the case is because software is a weird thing. It's unusually fragile. There's not much in human experience that's as strange as software. But one thing that is as fragile, though not as complex, is accountancy. And they solved that problem hundreds and hundreds of years ago, 1340 in Genoa, or the Romans in about 55 AD, depending on which account you read. But double entry bookkeeping is about is an error detection protocol. If you've got something as fragile as software, where a single small mistake can invalidate it, then you need error detection. You need a mechanism, a repeatable mechanism for detecting errors. In accountancy, they invented double entry bookkeeping, so you've got independent path verification of your ideas. Our version of that is test-driven development. We create a test, and that's one path, and then we write some code to meet the assertion that the test makes, and that's another path. That gives us an independent path verification of our ideas. There was a survey of software failures in production, an academic survey of thousands of projects, and they came to the conclusion that more than 70% of production failures are caused by the common kinds of mistakes that all programmers put into all systems, whatever their technology, language, framework, whatever, and they are eliminated by statement verification, by testing the statements that you make in the code. That's test-driven development. Test-driven development does that. So if you want to reduce your defect count in production by 70%, do test-driven development. I don't know of anything else that can do that at the same kind of level. So I think test-driven development will be around at some level, and my risky prediction is that when a kindergarten child learns to write her first line of code in 100 years' time, it will be done in the context of test-driven development, or whatever they call it by then. So far, I've kind of knocked all of the ideas that I come up with, but I think that there are some ideas that are durable, and I can't conceive of anything called software development, and certainly not software engineering, without them. And the first of those is iteration. Software development is an exercise in learning and discovery. That means that we need to maximize our opportunities to learn and discover. So we need ideas like iteration and feedback to be able to carry out test, evaluate more ideas. We need to work incrementally, so we need to modularize our system so we can work on different parts of it. We need to carry out experiments and think of ourselves as carrying out experiments to evaluate our ideas and see whether they're good or bad, using falsification to reject bad ideas. We need empirical discovery. We need to capture information from the real use and the production of our system and use that to inform the picture. I think that these will be absolutely cornerstones of whatever it is that we are doing, because these are the cornerstones of what it takes to do effective software development now. And these are foundational concepts. They're grounded in our need to learn and deepen our understanding. And I would argue that one of the cornerstones of our discipline is that it is this challenging learning. And if we are to become more professional, more effective at software development, we need to become world-class at the techniques of learning and discovery. And that's those sorts of techniques that were just on the previous page. So, yeah, I've just said this. So we need to optimize for learning and discovery. So my prediction is that even if it is the machines that are writing the code in the future, those 5 things are still going to be true. They're not going to be writing Gantt charts. You can bet that. They're going to be trying stuff out and figuring out what works. This is if you think about this, this is really applying kind of scientific style thinking to solving problems in software. You know, that's not going out of fashion anytime fast, even if it is the machines that are doing the creation. So software development in 100 years' time will be based on these ideas. And these are important, durable ideas. They represent big steps forward in quality and efficiency, and we can measure that. The State of DevOps report and the Accelerate book provide benchmarks that allow us to evaluate the impact of the application of these kinds of ideas in software development, and it's quite significant. In 1986, Fred Brooks wrote that there's no, a famous article. Fred Brooks was the author of the great book, The Mythical Man Month, which was published in 1970, and amongst other things had the very memorable phrase is that you can't make a baby in a month with 9 women. But he profoundly captured some of the problems at the heart of software development and applying kind of the wrong sort of production line thinking in the form of waterfall to solving problems in software. But in 1986, Fred wrote the famous article, There's No Silver Bullet. And to kind of paraphrase that, what he was saying is there are no 10 times improvements in productivity or quality to be had in technology or process in software. And that's an interesting idea. And I think it's probably true. And I think that what I've been saying so far probably is reinforcing that idea to some extent. But I think that there are mud bullets. I think there are 10 times worse ways of doing things. And our industry has not been very good at eliminating some of those 10 times worse practices. I would classify waterfall software development as one. Waterfall software development was applying production line thinking to a problem that is an exercise in learning and discovery. That's a terrible idea. You don't learn by laying out all of the steps along the journey. You learn by iterating, gathering feedback, experimenting, and so on. So if you can eliminate some of the dumb ideas, there are 10 times improvements. And we see that. There's data that shows that changes in practices can get you a 10 times improvement in software productivity if you're making mistakes. A good example of that is the HP LaserJet team in 2008. Go and look that up. There's a good book on that by Gary Gruber. There's another class of ideas that I think are important to think about and durable, and these are more technical ideas, perhaps, about the nature of the code that we create. I think modularity is deeply important, and one of the techniques that you can use to establish more modular systems is separation of concerns, making sure each part of our system is focused on solving one problem and solving it as simply and as straightforwardly as we can. Modularity allows us to draw lines and boundaries between different parts of the system, and then we can take advantage of ideas like information hiding, where we keep secrets between different parts of the system. I can make a change in one part of the system and not impact another, and that gives me freedom to move forwards with less stress. I've put loose coupling here. I think probably a better phrase is appropriate coupling, to make sure that our system is coupled to the minimum necessary degree in where it happens, and cohesion. The importance of getting the ideas that are related close together. My favourite description of good design comes from Kent Beck, and Kent says that good design is based on putting stuff that's related closer together and putting stuff that's unrelated further apart. So modularity and cohesion. And I think that's about as good as it gets in terms of describing what good design is about. So why I think is this important? Well, this goes back to one of the ideas that I mentioned at the start. We need to be able to fit the systems that we build inside a human head. So we need to decompose ideas that are bigger than will sensibly fit in our heads into pieces that are small enough so that we can fit them into our heads and think about them. Software development is about two things to my mind. It's about learning, and so ideas like experimentation, iteration, feedback are at the heart of that. And it's also about managing complexity. So modularity, cohesion, separation of concerns are at the heart of that. And if we apply all of those ideas, we get a better result. And I just don't see how they're going to go away, even over a span of time like the next 100 years. So my prediction is that in a period like 100 years, we probably are going to extend our cognitive function with machines. And even then, we're going to improve the capacity of our heads, but it's still going to be finite. And so even then, we're still going to need to compartmentalize to fit problems into our new expanded capacity. Software development is about learning and discovery, and humanity's best problem approach to learning and discovery is the scientific method. So applying the scientific method to solving problems in software is certainly going to work because that's humanity's best problem-solving technique. And so ideas like iteration, feedback, incrementalism, experimentation, and empiricism are at the heart of any discipline that we could think of as genuine engineering, and so enable us to build more complex, more sophisticated systems in future. One of the attributes of engineering is that it amplifies human capacity for solving problems. Software development is also about managing complexity, and humanity's best approach to managing complexity is to modularize, compartmentalize things and reduce the coupling between them. So ideas like modularity, information hiding, separation of concerns, loose coupling, and cohesion are absolutely central to that aspect of the problem. Those two are not going away anytime soon. The last of my candidates is continuous delivery. And yes, I am hubristic enough to include something that I was involved in popularizing in the list. And I hope with some reasonable reasons rather than me just trying to sell you a book or something. Why do I think this is the case? Continuous delivery is based on the application of the scientific method to software development. It's about concretely, consciously trying to achieve a more experimental approach to creating software repeatably and reliably. I think it's a very strong candidate for a genuine engineering discipline in the sense of applying scientific style rationalism to solving practical problems. I think it's a good candidate for that. The scientific method is humanity's best problem solving approach. It's not going out of fashion anytime soon, so it's certainly going to be around in 100 years' time. Continuous delivery has this at its heart: iteration, feedback, design, experimentation, and empiricism. Through automated testing and its support of that, continuous delivery encourages modularity, information hiding, separation of concerns, abstraction, and cohesion. I don't really have time to go into the detail of how automated testing encourages these things, but I strongly believe that they do. And if you check my YouTube channel, if you go to YouTube, search for continuous delivery, you'll find my YouTube channel. There are several videos that describe this idea in more depth. So my prediction is, even if the machines are writing the code in 100 years' time, they're going to adopt continuous delivery, or whatever it's called by then, but a more engineering approach to solving problems in software. Thank you very much.